To understand exactly what Mahout and MLBase bring to the table, it's valuable to once again define what is machine learning. Machine learning is the study and construction of algorithms that learn from and predict on data. Machine learning is a subfield of artificial intelligence and is sometimes also regarded as pattern recognition. While machine learning is a very broad field at this point, it can be described in generally two camps. You have classification and regression problems. In classification, you're trying to separate two groups or more groups of data, whereas in regression, you're trying to model the pattern of the data. There's definitely some other areas as well, but these are two very typical ones. On the slide, you'll see some other popular keywords having to do with machine learning. In machine learning, there's a very large demand for efficient mathematical optimization algorithms, as these allow us to converge to an optimal model. In order to do this, we generally use a lot of linear algebra routines, and so we will see that both MLBase and Mahout have efficient implementations of a lot of linear algebra routines. On this slide, you'll see a lot of typical applications of machine learning, which you have definitely been exposed to at some point. We have things like recommendation engines that recommend items to users, whether it's consumer products or movies or advertisements. We also often try to determine similarity between items. In banking or in the financial industry, we try to detect fraud or suspicious activity. You'll see several other examples on the slide, ranging from medicine to speech understanding.
Apache Mahout is a production-grade machine learning library. It has been developed by the Apache Software Foundation. The project was spinned off the Apache Lucidum project to provide distributed machine learning without the hurdles. It has been published under the Apache open source license that allows using the project, for example, in a commercial way. Mahout is available for free and can be set up easily on most of the big cloud processing platforms. The project focuses on robustness and real-world practical use cases. It focuses on scalability to give a future-proof solution and quality documentation to make integration into any project as easy as possible. Mahout has been developed using the MapReduce paradigm. It has been developed on top of the Hadoop distributed processing engine. It provided out-of-the-box machine learning, which means the applications were limited to what the developers thought about, at least without adding the original source code. But since spring 2015, no new MapReduce algorithms are accepted. In April 2015, with version 0.10.0, Mahout Samsara has been introduced. With Mahout Samsara, there was a major paradigm shift. Mahout is now more of a programmable environment that provides algorithms on different distributed processing engines. The first engine for Mahout Samsara was Spark, followed by H2O. They are currently working on the integration of the next engine, Apache Flink. Mahout Samsara gives API access to distributed machine learning algorithms via Scala interface. It also includes an R-like Scala domain-specific language to provide fully distributed linear algebra. As mentioned by a former developer, the idea is to make your own math using algebraic domain-specific languages. As components, there is the algebraic DSL, under which there is a logical translation layer that contains an optimizer to erase unnecessary computations. Then, these optimized processing pipelines are translated by a physical translation layer to be run on the processing engines, which means there is one translation layer per engine. And this way, the algorithms written in the DSL are executable on all supported processing engines.
MLBase is a project out of UC Berkeley's AMP Lab that was launched in 2012. With MLBase, the group had in mind to address two key issues. They wanted to build a platform suitable for an end user with potentially limited knowledge in machine learning, as well as researchers or experts trying to push the envelope. At the same time, they wanted to build a system that is good for prototyping, which nowadays is generally done on more non-scalable platforms such as MATLAB or scikit-learn, as well as for production, which requires robustness and scalability. MLBase can be seen as a stack of 4 components. On the bottom, we have Apache Spark, which we've heard a little bit about. On top of Apache Spark, we have MLlib, which is the collection of machine learning algorithms already optimized for distributed computing, offered as part of the Apache Spark project. On top of this, we have MLI. MLI makes it even easier for a developer developing machine learning algorithms to interface with MLlib. And finally, the arguably most interesting part of MLBase is the ML Optimizer. It allows a user with little to no knowledge of machine learning to learn to train a classifier with just a few lines of code. ML Optimizer optimizes on 3 levels, namely query optimization, runtime optimization, and the entire system runs on a distributed processing platform which is well suited for the type of data access patterns that is seen in machine learning. To better understand what MLBase has to offer, it helps to discuss its 4 primary focus points. The first of which is the easy declarative language, which is used for specifying machine learning tasks. This language has been designed to resemble languages which data scientists and statisticians are already comfortable working with. The second point is the intelligent optimizer, as mentioned before. The optimizer leverages best practices as well as statistical cost-based models to optimize model selection, parameterization, featureization, and other model configurations necessary for a training session to occur. This avoids exhaustive grid search while still collecting an optimal set of models to train. After model configurations have been trained on a subset of data, only the most promising models then train on the entire data set. The third point is that the system answers fast and early. This means that as soon as a computing node is finished training its model, it reports the results to the master, which the user can see, as well as that the system optimizes its learning plan based on these results, potentially training other configurations as a result of it. Finally, we have the distributed runtime, which is optimized precisely for the types of data access patterns which are typical in machine learning. In MLBase, a machine learning task is realized in 3 stages. We start with the declarative learning language, which a user uses to specify a task at hand. This language is then translated into a logical learning plan. The logical learning plan is a generic representation of all combinations of parameters, featureization techniques, algorithms, and more, which are going to be taken into consideration in this training session. The optimizer then transforms this logical learning plan into a physical learning plan. In the physical learning plan, we have specific sets of parameters to consider, as well as a specific set of models that we would like to train. As mentioned, optimization is performed on several levels, one of which being query optimization. In query optimization, the execution time of algorithms, as well as perceived performance estimated based on statistical models and best practices, can be used to optimize the training session. For example, normalizing features to a -1 to 1 range is known to improve performance of SVMs, so this may be incorporated in training sessions involving SVMs. On the contrary, AdaBoost is known not to be very robust to outliers, so MLBase detecting outliers in a dataset would immediately ensure that AdaBoost would not be present in that training session. Further, runtime optimization is used to further optimize the training process once it has begun. Computational guarantees and consistency requirements can be taken advantage of to speed up the training session. For example, asynchronicity and/or heavy subsampling can be taken advantage of. Gradient descent is an optimization algorithm present in several other higher-level machine learning algorithms. Fortunately for gradient descent, it is very robust to noisy gradient information and also to failed nodes, for example, in a distributed environment. This makes it an optimal algorithm to take advantage of these types of optimizations. According to the paper released by the AmpLab group on MLBase, gradient descent has been shown to even converge faster in the presence of weak consistency requirements. Finally, to understand MLBase's execution pipeline a bit better, we present this graphical representation of an example execution. The first 4 tasks are performed on a master node. Here we see that data is first loaded, we then downsample to 10%, perform, for example, standard feature normalization, but may be different depending on the training session, and generate, for example, 10 folds. These folds are stored for later retrieval, as well as distributed to each of the computing nodes. In addition, each computing node gets a unique model configuration with some parameterization. The computing nodes then train these model configurations and report the model summaries as soon as they finish to the master. The master reports this as it's occurring to the user, as well as waits until an optimal model has been determined. Finally, the master trains this most promising model on the full dataset and performs a sanity check. This concludes the training session.
When selecting a system for a specific use case, one has to decide, are you trying to create a prototype or a product that relies on robustness? Do you need more influence on the optimization process or independence of the processing engine? Is the setup process a hurdle? Do you want to get in touch with a machine learning algorithm at all? In any case, you can count on the high-level domain-specific language, and if you decide to use Apache Spark, you can count on MLlib too. These distributed machine learning libraries will give you the capabilities to leave the struggles of implementing a complicated distributed machine learning algorithm behind and focus on the goals you want to achieve.